We now have a fair understanding of what we mean by linear functions from Rn to Rm. Now we can extend this and ask similar questions for functions f from C to C. Can we talk about linearity for functions f from C to C? And if yes, what would be linear functions? Now from our discussion so far, we can look at three possible ways of defining linear functions. First, we can define linear functions to be functions of the form f of z is equal to alpha z. And in this case, we would want alpha to belong to C because we are just looking at homogeneous polynomials of degree 1. And these are precisely the homogeneous polynomials of degree 1 with complex coefficients. Or we can call functions that take lines to lines as linear. And this is similar to what we had seen earlier. And finally, we had the other definition of linearity, namely that a function f is linear if f of x plus y is equal to f of x plus f of y, and f of alpha x is equal to alpha times f of x. We can use this definition also for functions f from C to C, as we can add two complex numbers and we can also multiply a complex number by a constant. Now whether this constant should be real or complex is a question that we need to address. And the answer would come from the relationship between these three definitions, definition 1, definition 2 and definition 3. But before we go into this, we perhaps might have to recall what complex numbers are. So let us first recall what complex numbers are, familiarize ourselves with complex numbers, and then understand these concepts better. We know that there is no real number such that x squared plus 1 is equal to 0, or in other words, x squared is equal to minus 1. If such a number existed, we would call it square root of minus 1, because this number when squared you get minus 1. So it's generally said that just like how we went from rational numbers to irrational numbers because we were interested in square root of 2, we went from real numbers to complex numbers by denoting the square root of minus 1 as I. And complex numbers are numbers of the form x plus iy, where x and y are both real numbers. Now, we did not start studying square root of 2 just for thrills. We were interested in it because they arose naturally. More precisely, if you take a right angle triangle with two of its sides of length 1, then the hypotenuse would be of length square root of 2. And this was the reason why it made sense to study square root of 2. So there is a natural question that we can ask here. Is there a similar reason to study I? Now, there was not for a very long time, and that is why I was called imaginary. And this name still sticks. Okay, the x is called the real part of the complex number and the y is called the imaginary part of the complex number. Because in some sense people believe that this number does not exist in nature. And for the same reason there was a lot of opposition to accept complex numbers. But finally it got accepted, and the story of why it got accepted is very interesting. People were interested in finding the roots of cubic polynomials. In other words, they were interested in finding real numbers x which satisfies the equation ax cube plus bx square plus cx plus d is equal to 0. Where a, b, c and d, all these numbers are real numbers. So there is no complex number at this point. Now, interestingly, a mathematician named Cardano showed that if you assume the existence of these imaginary numbers, then you can find a real root to the cubic polynomial. Therefore, complex numbers helped us understand something about real numbers, and it is this phenomenon that made complex numbers important. Therefore, people started studying set of numbers of the form x plus iy such that x comma y are real numbers. And this collection of numbers were called complex numbers. And in some sense, numbers are interesting because we can add and multiply them. So the question is, how do we add or subtract two complex numbers? More precisely, how do we add x1 plus iy1 and x2 plus iy2? The answer is we will add the real and imaginary parts separately. That means we look at x1 plus x2 plus I times y1 plus y2. And this is the sum of the two numbers x1 plus iy1 and x2 plus iy2. Now, how do we multiply two numbers x1 plus iy1 into x2 plus iy2? Now, assuming that multiplication and addition for complex numbers also satisfy all the nice properties like associativity, distributivity, etc., we can just expand it out. We can look at x1 x2 plus I times y1 x2 plus I times x1 y2 plus I square times y1 y2. Now we use the identity that I square is equal to minus 1. We can rewrite this as x1 x2 minus y1 y2 plus I times y1 x2 plus x1 y2. So in this manner, we can multiply two complex numbers. Now we want to show that the addition and multiplication that we defined are in some sense nice. Namely, they satisfy properties of associativity, commutativity, distributivity, etc. that are satisfied by real numbers. And recall that we defined multiplication of complex numbers motivated by these properties. Therefore, it is no surprise that addition and multiplication of complex numbers satisfy these properties. However, we need to check it. But this is a simple process and I leave the checking as an exercise. But let us just go through these properties. Namely, addition of complex numbers is associative, or the order in which you do addition does not matter. Second, there exists an element 0 or additive identity which when added to any complex number, you will get the complex number itself. And for every complex number, you can find another complex number such that if you add the two numbers, you get 0. This number is called the additive inverse of z, and sometimes it is denoted as minus z. In fact, we already know what this w is. If z is of the form x plus iy, then w is minus x minus iy. We also want our addition to be commutative. So these are the four properties of addition, and then we have similar properties for multiplication. Multiplication is also associative. Multiplication is also commutative. Moreover, just like we had additive identity, we have a multiplicative identity, and the property is that this when multiplied with any number, you get the number itself. Once again, it is easy to see what this multiplicative identity would be. It is a number of the form 1 plus 0i. Also, given any z in the set of complex numbers, we want a multiplicative inverse for it. That means we want a w such that z into w is equal to 1. It's a little more tricky to find out the form for w, but I leave it as an exercise. Similar to what we saw earlier, the multiplicative inverse is often denoted as 1 by z. And finally, we have distributivity, which connects the two operations addition and multiplication. Now, I leave it to you to check that complex numbers satisfy all these properties. Now, notice that as C is the set of all x plus iy such that x comma y belongs to R, there is a natural map from C to R2. Namely, the map that takes x plus iy to x comma y. And because of this map, now we can visualize the set of complex numbers as a plane, where each point x comma y is a complex number. So the point x comma y is the complex number x plus iy. And this is called the complex plane. And once we have this visualization of the set of complex numbers, then we can talk about lines. And once we have lines, we can talk about functions that takes lines to lines, and therefore we can talk about linear functions, etc. And therefore this visualization of the complex plane is a very important part of our understanding of the set of complex numbers. And with this, we have completed most of the basic properties of the set of complex numbers. Having understood complex numbers, now we can look at functions f from C to C. And we can in particular look at functions of the form f of z is equal to alpha z, where alpha is a complex number. Now we want to see if such a function takes lines to lines. But notice that the complex number z can be written as x plus iy, and alpha can also be written as, say, alpha 1 plus I times alpha 2. Therefore, alpha times z is equal to alpha 1 plus I alpha 2 into x plus iy, which we know is equal to alpha 1 x minus alpha 2y plus I times alpha 2x plus alpha 1y. Therefore, if we visualize this function as a function from R2 to R2, I'm calling it f tilde because it's not exactly the same as f. It takes the point x comma y to a point alpha 1x minus alpha 2y, comma alpha 2x plus alpha 1y. Now observe that such a function takes lines to lines. That is something we have seen already. And therefore, the function f of z is equal to alpha z should also take lines to lines. We saw that functions of the form f of z is equal to alpha z take lines to lines. Now we ask the reverse question. Suppose a function take lines to lines, is it of the form f of z is equal to alpha z? As usual, you should pause the video and ponder about this question before going ahead. Let us now answer this question and see if it matches with what you had discovered yourself. Consider the function f tilde from R2 to R2 defined as f tilde of x comma y is equal to x comma minus y. Now notice that this function takes lines to lines, and therefore the similar function f from C to C defined as f of x plus iy is equal to x minus iy should take lines to lines. However, I claim that this function is not of the form alpha 1 plus I times alpha 2 times x plus iy. I wouldn't go into the proof of this, but it is just a computation and I leave it as a homework. More precisely, I want you to show that there does not exist alpha 1 and alpha 2 such that alpha 1 plus I alpha 2 into x plus iy is equal to x minus iy. Therefore, we see that not every function that takes lines to lines is of the form f of z is equal to alpha z. Now notice that the function f of xy is equal to x comma minus y is reflection with respect to the x-axis. Similarly, you can show that if you take any line and take the reflection with respect to that line, then this function will not be of the form f of z is equal to alpha z. And actually a more general result is true. That means if we avoid reflections in some sense, which I cannot make precise at the moment, then all the other linear maps has the form f of z is equal to alpha z. Let us now look at another property of this function. It is very easy to check that f of z1 plus z2 is equal to f of z1 plus f of z2. It is also easy to check that f of alpha z is equal to alpha times f of z if alpha is a real number. However, if you take f of iz, this is equal to f of ix minus y, which is equal to f of minus y plus ix, which is equal to minus y minus ix. On the other hand, I times f of z is equal to I into x minus iy, which is equal to ix minus I square y, which is equal to y plus ix. And clearly these two are not equal to each other. Therefore, if you want f of alpha z to be equal to alpha times f of z for complex numbers alpha, then this function is not linear. So notice that our function is linear with respect to the third definition that we are interested in, that is a function such that f of z1 plus z2 is equal to f of z1 plus f of z2 and f of alpha z is equal to alpha times f of z if we take only real values for alpha. However, if we allow complex values for alpha, then this function will not be linear with respect to this definition. Therefore, if we want to avoid calling this function linear, then we should allow alpha to take complex values. In other words, if we want our linear function f from c to c to have the simple form f of z is equal to lambda times z, then we should force it to satisfy the condition f of alpha z is equal to alpha times f of z for complex numbers alpha. See, it is nice when our functions have simple form. Moreover, such functions do take lines to lines. So maybe we should stick with this as our definition of linear. In other words, we should call a function f from c to c linear if and only if f of z1 plus z2 is equal to f of z1 plus f of z2 and f of alpha z is equal to alpha times f of z for alpha being complex numbers. Let us now try to understand geometrically what extra properties such functions have in addition to taking lines to lines. But before that, let us simplify things a bit. See, we certainly want f of alpha z is equal to alpha times f of z for all alpha that are real. Now, if in addition, if we have f of iz is equal to I times f of z, then notice that these two together imply that f of alpha z is equal to alpha times f of z for all complex numbers alpha. Therefore, all we are asking extra is that f of iz is equal to I times f of z. And we will understand the meaning of this geometrically. The first step in this process is understanding the function f from c to c defined as f of z is equal to I times z. We will see what this function does. Notice we can rewrite this as f of x plus iy is equal to I times x plus iy, which is equal to ix minus y. So if we imagine this function as a function f tilde from R2 to R2, then the function is of the form f tilde of x comma y is equal to minus y comma x. Now convince yourself that this function f tilde is the map that rotates R2 by 90 degrees in the anti-clockwise direction. I will give you some pointers to start thinking. Notice that the x-axis goes to the y-axis, the y-axis goes to the x-axis, and notice one more thing. Whatever is in the positive x-axis goes to the positive y-axis, but whatever is in the positive y-axis actually goes to negative x-axis, and whatever is in the negative x-axis goes to whatever is in the negative y-axis. But whatever is in the negative y-axis actually goes to positive x-axis, and so on. Similarly, you can also see that if you take the line y equal to x, that gets mapped to the line y is equal to minus x. So now you work a little bit more and convince yourself that this function f tilde is the map that rotates R2 by 90 degrees in the anti-clockwise direction. Observe that we already saw that functions f from c to c such that f of x plus y is equal to f of x plus f of y and f of alpha z is equal to alpha times f of z for all complex numbers alpha are equivalent to functions f from c to c such that f of x plus y is equal to f of x plus f of y, f of alpha z is equal to alpha times f of z for all real numbers alpha, and f of iz is equal to I times f of z. Now notice that these two conditions meant that the function take lines to lines. On the other hand, this condition says that this function commutes with rotation by 90 degrees. In other words, whether you first rotate by 90 degrees and then act the function, or you act the function and then rotate by 90 degrees, you should get the same answer. Now observe that reflection has this property that if you first reflect and then rotate, or first rotate and then you reflect, you will get different answers. And that is precisely why reflection did not satisfy this definition. And therefore functions f that has the simple form f of z is equal to alpha z not only takes lines to lines but also commutes with rotation by 90 degree. So that is the property of functions with this form, and it is such functions that we will call linear when it comes to functions from C to C. And often to distinguish it from linear maps from R2 to R2, we would call it complex linear. And once we understand linearity of functions f from C to C, it is easy to generalize it to functions f from Cn to Cm, where Cn is the n-fold Cartesian product of C. That means C cross, etc. n times. How do we define linear functions f from Cn to Cm? We say a function f from Cn to Cm is linear if f of x plus y is equal to f of x plus f of y and f of alpha x is equal to alpha times f of x for all alpha in C. So this is the definition of linear functions from Cn to Cm.